Yes, good luck.
Okay. Thank you, Mars, for the kind introduction. Good afternoon. My name is Filippou Christiana. I'm from Cyprus. I'm a PhD candidate at Cyprus University of Technology. My supervisor is Professor Christos Chrysostomou. Today, I will present part of my PhD research, which is focused on the modeling of the behavior of a Masonry-infilled RC frame. In the next slide, you will see some information regarding my university. Cyprus University of Technology was founded in 2004. It's a new state university in Cyprus. It is growing within the historical center of Limassol city, and it has become a point of reference in Limassol. Cyprus University of Technology, CUT, offers quality and competitive degree programs, especially 17 undergraduate and 32 graduate programs. Cyprus University of Technology have 3 departments in engineering technology, electrical engineering and computer engineering, and mechanical engineering and material science, and civil engineering and geomatics. Cyprus University of Technology is an innovative university with international recognition, which promotes excellence in education and research. In less than 11 years of operation, the Cyprus University of Technology has occupied 5 positions in international rankings. Specifically, in 2017, the Cyprus University of Technology is ranked among the top of 300 and 350 universities worldwide. In addition, the Cyprus University of Technology is ranked in position 63 in top of new universities in the world. CUT is constantly committed to promoting research excellence and is internationally distinguished in this area, providing a total of 40 million euros of external funding for 227 research programs. So in this webinar today, the scope of the research and small introduction regarding the modeling of Masonry-infilled RC frame will present. Also details about the experimental case study that it is selected for verification purposes are presented. In addition, the third part of this presentation has to do with how the model of Masonry-infilled RC frame is developed in Diana finite element software. Also in this presentation, the model results are compared with experimental results, and finally some outcomes and future research are presented. Masonry-infilled RC frame is a composite frame comprising of 2 interacting structural components of different materials with different structural behavior and failure mechanics. In the literature, different techniques that simulate the behavior of infill wall can be found. The techniques are divided into 3 categories, namely micromodeling, mesomodeling, and macromodeling. Several numerical studies have been carried out to investigate the behavior of Masonry-infilled RC frame under earthquake loading, but some deficiencies still exist. Therefore, there is a need to develop an accurate numerical model to capture the behavior of Masonry-infilled RC frame under cycle loading. To conclude, there is a need to simulate the nonlinear behavior of Masonry-infilled frame due to material nonlinearity and complexity in the relative behavior between frame and wall. In order to develop an accurate model, there is a need to model the nonlinear behavior of the interaction between Masonry-infilled and frame. In general, in Masonry structural model, we can make the assumption of full bond between layers for simplicity purposes, but can be unrealistic due to possible slip deformation at the interface between the frame and the infill wall. In addition, the numerical characterization of the surface element and discretization of the wall surface in finite elements it is important for Masonry structural model. In addition, division of the infill wall into numerous surfaces elements leads to accurate results, represent the local failure in detail, and intensive computational requirement. Therefore, the scope of this work is to assess the efficiency of a finite element model as a numerical tool to simulate the Masonry-infilled RC frame in plane behavior under cycling load. In the next 2 slides, we will see the steps that are followed in order to achieve the scope of this work. First of all, An appropriate experimental case study is selected for verification purposes. Then, literature review regarding the experimental and analytical studies on the behavior of Masonry-infilled frame has been done, and the literature review regarding Diana manuals and reports has been also done. After that, the geometry of the specimen was created in Diana, similar as possible to experiment. The geometry about the dimension of concrete, the dimension of masonry members, reinforcement, bar, location, cross-section, etc. In order to model this type of structures, suitable numerical constitutive models of each component of masonry-infilled RC frame were identified. In addition, the required parameters for the constitutive model of each component of the structure were selected. After the selection of the required parameters, the load is applied to the model to simulate the load of experimental case study using displacement control analysis. After the development of the numerical model, age and value structural nonlinear analysis were performed. The efficiency of the simulation model was assessed using the results obtained from the experimental case study that was selected for verification purposes. It is important to mention that in order to achieve reasonable results between numerical results and experimental results, some of the material and mechanical properties, especially material properties from masonry and frame interface, are taken from the Diana software manual or from the available literature. Now we move to a short description about the experimental case study. The experimental case study that was selected, it was carried out by Kudas at University of Patra and studied the effectiveness of seismic retrofitting of existing masonry-infilled RC frame with strengthened material called textile reinforced mortar. A short description of the experimental case I will present it to you. As you can see, this figure was 2 out of 3 scale 3-story structure with no seismic design and detailing, subjected to in-plane cycling loading. 2 masonry frames were designed and built with and without strengthening material. Today, the description of the masonry frame without strengthening material is presented. As you can see in this figure, the test specimen had total height of 6 meters, and each story was 2 meters height, and between the edges of the column had span 2.73 meters, as you can see in this figure here. The columns were rectangular and cross-section, and beams were tuff section. The longitudinal column reinforcement has 12 millimeter diameter. The transverse reinforcement for concrete members has 6 millimeter diameter smooth steel. You can see the thickness of the infill. The wall was supported rigidly by the RC foundation being placed at the bottom of the frame. Full details about this experimental case study can be found in the article of Kudas et al. In this figure, you can see the mechanical properties of the concrete, of the masonry, and for the reinforcement. You can see the class of concrete was used with a value of compressive strength of concrete equal to 27.8 megapascal, and the modulus of elasticity of concrete was 24.1 gigapascal. You can see the class for longitudinal reinforcement, and you can see also the class for transverse reinforcement. The transverse reinforcement for concrete members was class of S220 with mean value of unit strength equal to 270 megapascal. Compression diagonal tests were performed in order to define the compressive strength, modulus of elasticity, perpendicular to the bent joint, and the cracking strength, as you can see in this figure. The compressive strength of masonry was 5.1 megapascal, and the elastic modulus of elasticity of masonry perpendicular to the bent joint was 3.37 megapascal. You can see the general view of the test setup. Pre-stressing rods were used on the foundation beam of the specimen to provide full clamping of the specimen with a laboratory floor. The gravity load was equal to 80 kilonewton per story in order to represent the fraction of the permanent load due to lateral loading action. 3 actuators were mounted on the specimen, as you can see, 1 per story, to impose the 5 cycle of loading. A total of 5 cycles of loading were finally applied to Masonry-infilled RC frame, and an inverted triangular distribution of forces to all 3 floor levels were kept until failure occurred. Free vibration test was performed in bare and in Masonry-infilled RC frame to identify the experimental fundamental period of the structure in each phase of construction. In order to perform the free vibration test, the specimen is subjected to static displacement at the top of the specimen. In this table, you can see the fundamental period for bare frame and for Masonry-infilled frame. After the free vibration test, cycle test was performed. The maximum base shear force was obtained during the 3rd cycle of loading of the arret of the specimen. After the 3rd cycle of loading, the lateral strength was decreasing due to local crashing at the 1st story of the infill. During early loading in Masonry RC frame, a cracking pattern was developed, as you can see in this figure: horizontal cracks in the corners, diagonal cracking in the middle of the infill, and step-type crack also developed. The frame infill separation occurred at a very early stage of loading. The peak value of measured gap opening was 2 mm for the 1st story, 1.5 from the 2nd, and so on, you can see. Now we'll move to the model of the structure. In order to model the Masonry-infilled RC frame, the Diana finite element software was selected. This type of structure was implemented in Diana using available materials, section, and element commands. In this model, rigid foundation is considered, and 2D model representation is used. The pre-stressing rock were simulated as the dead axial load. The infill wall was simulated with same thickness as the 2 individual walls, separated by 60 mm gap that were built in the experimental case study. T-beams is simulated as a rectangular beam. You can see the units that were used for the model. In addition, the geometry was the same as possible with experimental case study. You can see also the boundary constraint at the base of the model, where is X and Y transition. Diana offers a range of elements times for modeling structure made of brittle materials. The concrete frame and Masonry-infilled were modeled with 8-node plane stress elements. The column and beam have 170 mm width, and the masonry has 110 mm thickness. The total number of elements was 3,162. In addition, the steel reinforcement in the frame was modeled with 2-node bar elements, and they were connected to the 8-node concrete element at the 2 external loads, as you can see in this figure. The cross-section area of the bars are Y10 for the longitudinal and Y8 for the stirrups. Figure below, you can see both elements, the plane stress and the 2-node bar elements. The interface between an infill wall and the frame was modeled by 3-point line interface element capable of modeling cohesion, separation, and the cycling behavior of the interaction between frame and infill wall. The width of the interface was the same with the masonry, equal to 110 mm. In addition, point mass element is used for agent value analysis to simulate the dead load. In total, 12 point mass elements were used in the model. In this case study, the shape of the 2D elements were kept rectangular with nearly equal size, as you can see this figure. In this figure, you can see the 12-point mass element that were used, the 8-node plane stress element for modeling the concrete frame in masonry, and a 3-point line interface element capable of modeling the interface between frame and the wall. You can see also in this figure the width of the interface and for the beam and the columns, and the cross-section area of the longitudinal and transfer reinforcement. Now we move to the material models. 4 material models are considered in this numerical model to represent the nonlinear behavior of concrete, steel reinforcement, masonry, and that of interface between masonry and frame. The concrete material model that was chosen is the total strain crack model. The total strain crack model describes the tensile behavior of concrete, and Magawa-Fukuda model describes the compressive behavior of concrete. As you can see here, you can see the cyclic behavior of concrete. Beside the definition of basic parameters like Young modulus, the total strain crack model requires only a small number of engineering parameters, such as the tensile strength, the compressive strength, as you can see in this figure, and the fracture energy in tension. This model has no ability to reduce. This model has no ability to reduce the stiffness due to early cracking of concrete section, and therefore the modulus of elasticity was reduced. In addition, the tensile strength and the fracture energy were obtained from the empirical equation according to FIB model code 2010. The Menegotto-Pinto model was chosen for cycling behavior of steel reinforcement. This table shows the basic parameter in order to specify the Menegotto-Pinto model. You can see the modulus of elasticity, the yield stress for longitudinal reinforcement, and for steels. The Masonry-infilled material model that was chosen is the engineering masonry model, which is a mere failure model that covers the tensile, shear, and compression failure modes. The shear failure mechanism based on the standard Coulomb friction failure criteria is included in this model. As you can see from this table, the engineering masonry model requires a large number of engineering parameters, and most of these parameters were not measured in experimental case study. The direct input parameters that are necessary to apply the engineering masonry model as implemented in Diana software are shown in this table. These materials parameters were taken from the literature. For example, the compressive fracture energy and the tensile fracture energy were calculated according to the recommendation proposed by Rhodes. In addition, the cohesion was obtained 1.2 to 1.5 times greater than that of tensile strength according to the relation that proposed by Serre. The engineering masonry model have 4 options for cracking behavior for the head joint failure. In this case study, the head joint failure not considered option was selected due to the fact that in the case of selected crack option, the results are less realistic with overestimation of capacity and energy absorption. An interface gap model, plasticity based and proposed by Renzo, was used for the interface element, describing the connection between masonry-infilled wall and bounding RC frame. The model includes tension cutoff for tensile failure and Coulomb friction envelope for shear failure. In this table, you can see mechanical properties for this model. In this study, a recommendation by Diana, which is based on the equation proposed by Renzo, is used for calculating the value of normal and shear stiffness, as you can see here. In addition, the cohesion associated with the Coulomb friction interface model has been determined based on the relation proposed by Sarkozy et al., as you can see in this slide. You can see the interface normal modulus and the longitudinal. It is important to mention that one drawback regarding the use of this interface model is the lack of material properties, as no data were available regarding the behavior of interface between masonry-infilled and frame. Therefore, it was decided to define the material properties of the interface by fitting the numerical results to experimental results obtained from the experimental case study. Now we move to the type of loading and constraint. The model was loaded with constant axial load on the top of the column equal to 150 kilonewton per meter to simulate a dead load, as you can see here. The loading process during the numerical analysis was simulated as closely as possible to experimental loading by using point prescribed deformation load at the top of each floor, as you can see in this figure. The load has value 1 millimeter and it is posed at the top of each floor, as shown here. Certain load combinations are created in order to capture the actual deformation load at each cycle of loading. All nodes at the bottom of the lower of Mason-infilled frame were restrained in X and Y direction in order to simulate the strong foundation beam that was used in experimental case study. Two types of analysis were performed, age of value analysis and nonlinear cycle analysis for Mason-infilled RC frame. Therefore, material nonlinear analysis was performed with secant iteration scheme and automatic incrementation procedure in which both the number of steps and the corresponding step size are automatically computed. The energy-based conversion criteria was applied with these standard tolerance values. Now we move to finite element model results. The result of age and value analysis are presented in this table. This figure shows the model shape for bare frame and for Mason-infilled frame. You can see the fundamental period for bare frame and for Mason-infilled frame. The computed values of the fundamental periods are compared and presented are great correlation to the experimental one, as you can see in this slide. Now we move to the structural cycle nonlinear analysis. A comparison of the base shear versus top floor displacement obtained during the experimental study and numerical analysis of Mason-infilled RC frame are shown in this figure. The experiment is with a black line and numerical analysis with a red line. In addition, the global results in terms of base shear relation to the load step and top story displacement versus load step for specimen are presented here. And discrepancy appears in the last cycle of loading, as you can see here. The shear force capacity and energy, the energy is calculated, the area enclosed on the loop in the base shear versus displacement diagram are overestimated compared to the experimental results. This may be attributed to high nonlinearities that are introduced at that stage during the experiment. Based on the result, the base shear of the loading direction is underestimated about 5%, but in the loading direction, the base shear is overestimated 10% at the fourth cycle of loading. The energy at the last cycle of loading, as you can see, is overestimated about 20%. This figure shows the comparison between experimental numerical results for Mason-infilled frame in terms of global lateral stiffness and hysteric energy, respectively. The second stiffness degradation of the model is calculated according to these equations. In addition, for easy calculation, the evolution of the energy of the model is expressed by this calculation, these expressions you can see here. From the figures, it is apparent that there is a good agreement between the numerical and experimental results for Mason-infilled frame regarding the initial stiffness, ultimate stiffness, shear capacity, and energy in a cycle of loading and unloading. In this slide, the figure shows the cracking that occurred at the first floor during the fifth cycle of loading and unloading for Mason-infilled RC frame in the experiment and the model. In addition, in this figure, you can see the damage at the first floor after the end of the test for the experiment and for the model. This figure shows that the crack pattern in terms of orientation and location and the damage in the numerical model are the same as those observed in the experiment. In this slide, you can see the distribution of the shear stresses over the infill wall during the third cycle of loading. You can see clearly the diagonal strut develops within the infill at the first and second floor. In this figure, you can see also the shear stress distribution over the infill and during the fifth cycle of loading. It is clear that the majority of the damage is concentrated on the first floor. Here you can see a small video, the evolution of the shear strength over the infill after the third cycle of loading. It is clear that the majority of the damage and energy is concentrated at the first floor. Also, you can see flexural horizontal cracks and tensile vertical cracks develop, which are reasonable for beginning of the nonlinear behavior. You can see the diagonal strut, how it is developed. The complexity of the simulation of Masonry-infilled RC frame also increases because in the model, the interaction between infill wall and frame must be taken into account. The behavior of the interface between infill wall and frame depends on infill wall frame relative stiffness and wall frame friction and bond strength. In order to capture the local interaction between RC frame and infill wall, an accurate evaluation of the interface engineering properties is required. This figure shows the comparison of the results of the numerical model of Masonry-infilled RC frame, including the infill wall frame interface with the red line and with full continuous connection between the frame and the infill wall with the gray line, in terms of base shear versus top floor displacement. From the analysis of the graph, it can be concluded that the introduction of interface element is beneficial in comparison to continuous connection between frame and the wall. The introduction of interface element between frame and the masonry significantly influence the overall behavior of the masonry. You can see that we have lower strength, lower stiffness, and lower energy absorption. Therefore, more accurate simulation of Masonry-infilled RC frame can be achieved by using interface element taking into account the interaction between masonry and surrounding frame. The local results obtained from the Masonry-infilled RC frame model are described in terms of gap opening between infill wall and RC frame. This figure shows the comparison between experimental with a black line and with a model result red line for the gap opening of the interface on the first floor at 4 different positions. There's a good agreement between numerical and experimental results in terms of gap opening. For example, the peak value of gap opening between beams and infills at the first floor was 1.2 millimeter in the experiment and 1.9 millimeter in the numerical model. This figure shows the value of gap opening between the wall and the frame at the 3rd, 4th, and 5th cycle of loading. From the figures, it is apparent that there's a good agreement between numerical and experimental results in terms of gap opening. Now we move to some conclusion. The numerical model could simulate the in-plane nonlinear behavior of a Masonry-infilled RC frame with good accuracy in terms of fundamental period, initial stiffness, ultimate stiffness, maximum shear force capacity, energy, crack patterns with respect to the location and orientation. In addition, the gap opening between infill wall and RC frame, the numerical model, and the experiment has been compared and presented an analytical correlation. In particular, the energy and the maximum shear capacity in the last cycle of loading is overestimated compared to the experimental results, which may be attributed to high nonlinearities at that stage during the experiment. The calibrated model of Masonry-infilled RC frame will now be used to perform numerical experiments through parametric study to investigate the influence of the mechanical properties of the infill wall in the strength, in the stiffness, and in the lateral capacity of Masonry-infilled structural system. These results will contribute to the investigation of a general model for the application and then design of Masonry-infills in existing RC frames. In addition, this calibrated model will be used for parametric study of the behavior of Masonry-infilled frame with openings. Thank you for your attention.